This is the 2016 higher level short questions. It's question 1A, so it's related to a truncated cylinder, meaning it's been cut off. It's a cylinder that's been cut off at an angle. We basically have a drawing that shows the elevation of the completed shape. So this is our cylinder with the curves and straight section cut off it. It looks like a circle in end view, and we have to find the surface development and plan. I'm going to start with the end view, and I'm going to label the points 1, 2, 3, 4, 5, 6, 7 and 8. So we've got 8 points on this curve, and we're going to basically take them straight across. So they've given us some of them in the elevation. We've got point 1 already, we've got point 2 already, 3 is here and 4 is there. We don't have all the other points, so I'm going to take those across now. Just bring in 5, 6, 7, 8 across to elevation and label them. This is very much like a Junior Cert question. So we have to find the surface development. For a surface development, we always need the true width and the true length. So what I mean by that is the true length of the top surface 1 is here. So in other words, I can take that, for example, from elevation with my compass and bring it down to plan, and that gives me the point 1. Same thing with 2. I can take the length of 2, bring it down to plan, and that gives me my length of 2. The distance between the lines, I see those in the end view. So distance from 1 to 2, 2 to 3, 3 to 4, you'll see it here 4 to 6, and 6 to 8 are all equal. So when I come down here, I know that this line here, I've got the distance here is 1, it's the center one. I know when I take this point down, here's the line 1, 1. So I have the distance to 2, to 3, to 4, to 6, and to 8, but I'm not going to label those yet. I'm going to take them one by one. I've got the first 4 points, and then I'm going to take the smaller distances, 4 to 5, 5 to 6, 6 to 7, 7 to 8. So when I come along, I've got the distance from 4 to 5 to 6, which is already there, to 7 and to 8. So I have the position of those lines. I'm going to draw in construction lines to show all those. Okay, so I've drawn in the position of each of those lines. Now, I've got all of my lines 1 to 8 drawn in. I can come along and take them individually, in other words, by taking the distance for 3 and bringing it down. But I can just use my set square and t-square and just bring the points down. Here's the point on 3 that I want, down onto line 3. 4, here's line 4. We have 5, here's the next one. 6, 7, and 8. And that gives me all of the points. I can draw in that curve. I can also find the points down below. So I could just do a simple version of an axial symmetry. So if I just bring the points down, and it'll give me the points as an axial symmetry. So in other words, here is my position for 8, and it's already going to be gotten for me because I have it down here. It's along the line. The reason I'm doing this as an axial symmetry is because I don't have to go find the line for 7 in the bottom part of the plan. I can just take point 7 and flip it straight over and find 7 on the line of plan. I come over to 6, flip it over, and the line will be down here in plan. So notice I have my construction line come down anyway. 5, same thing, just flip it over, and it's the quickest way to find the points. And then 4, 3, 2, 1, I can just bring straight down. And that gives me all of my points. I can join those all up for the curve. Part B of the question, we have to locate point P, which is on the cylinder. It's shown in the elevation. We have to locate it in the end view and on the surface development. So they're giving you a hint on how to do this. Point P on the end view is just brought straight across. Here's my point P. I'm going to highlight this line because this is an important line. Because I can just find this line in plan, and if I find this line or not in plan in the surface development, I can find the point P in surface development. And it's the same system, it's exactly what I've done already. 2 to 3 was that distance, 2 to P is this distance. So I can just come along and find 2 to P. So here's line 2, and just step up my distance. That lets me draw on the blue line in plan. Here is my blue line. Point P is on the blue line, so I can just take it straight down. And that is point P on the surface development. That is the question complete. Question A2. This is a pretty straightforward oblique planes question, and it goes through basically the basics of oblique planes. So we've got a bar chart. There's a little drawing of it here. We've got the plan and the incomplete elevation of it. We have to complete the elevation. The basic principle here is that lines parallel in one view are parallel in all views. So if I look here, I see the lines, all of these lines here on the sides of the bar chart are all parallel to the sides. All those lines are parallel to one another, meaning they'll be parallel in every view I ever draw. If I was going to draw elevation, plan, in view, auxiliary elevation, auxiliary plan, those lines would remain parallel. So that means I've got my edge, I can draw all those lines parallel to the edge in elevation. So what I'll do is I'll take each of these points on the bottom line, I have the bottom line, take each of these and bring them up to elevation, and I'll project lines parallel to the side. Here's my side, I'm just going to draw those parallel. I'll do that now. I've labelled my points 1 to 6, brought them up onto the line in the elevation. As I said, I'll take those 6 lines now parallel to the side. So number 1, 2, 3, 4, 5 and 6. And the actual side of the bar chart, the y-axis, is here in plan. I've got the position of all those lines. Now I can just take the points. So in other words, the side of the bar chart, I can just take this point up onto the line. Number 1, here's the end of 1, here's the end of 2, end of 3, end of 4 and 6. And I'm noticing this line here in elevation is horizontal, so meaning the top of each of these bar charts are just going to be horizontal because those are parallel to this edge. That edge is horizontal, meaning all of these lines have to be horizontal. So I can just take up one point on each of the lines and find those in the elevation. So I'll take up, for example, the y-axis of the bar chart, and there it is. I've drawn in the point. I'll take up point 1 up to elevation, and I find it on the line 1. Here I find it, and I know that it's a horizontal line, so I can just draw that in. I have the short bar of the bar chart drawn in. Same then, I can take the point here on 3, bring it up onto line 3. It's a horizontal line. So there is the horizontal line, and I can draw on 3 bars the exact same way. I've completed the 3 bars on the bar chart. Now there's a slight issue with this question, in that if you notice the lines coming from 2, 4 and 6 should hit the green diagonal, and you can see they don't. The second way to do this question would have been to take the point on the green diagonal and bring it up onto the green diagonal in elevation. That point would join back to line 6. You can see it there. The problem is that when you do that, it doesn't actually line up to the edge, which it should, because they're parallel in plan. So whether you were doing it the way with the points brought up onto the diagonal, or doing it the way I've just shown you, you can do it one way or the other. It doesn't make any difference. Don't worry that my way doesn't touch the green diagonal. So in other words, this point should be down here, but it'll be way off if it is. You can just complete it as I've done for part A. Part B then, determine the true inclination of the diagonal AB to the horizontal plane. So we've got a line AB. True inclination is the true angle. Horizontal plane is the ground. So they're asking in simple English, what's the true angle between the line and the ground? We've got 2 ways to do that. I can come out here and look in at 90 degrees with an auxiliary elevation. So I can project out here, parallel to my XY line, draw my auxiliary elevation out here, XY line. And then I can project out line A and line B. And then I can take my height for A, which is 0 in elevation. Here's the height of A. And I can take the height of B. So that's the straightforward way that we've done loads and loads of times already. Height of B, and I'd project out the height of B. And I'd get an auxiliary elevation with my true length of line AB. We've got simpler and quicker versions of that. So we said when you're dealing with just a line, what we can do is rotate the line so I'm looking in at 90 degrees. Meaning, at the minute I'm looking in here. So straight in plan. I can just rotate the line so that I'm looking in at 90 degrees. So what I can do is take the line AB, and I'll just rotate A around, and I'll draw it straight across. Now that is me looking straight in at line AB. So in other words, B stays where it is, A has moved around to here. I can find A in the elevation by just bringing it straight up, and again the height of A was 0, it'll come across. So I've taken A into a new position, swung around to here, brought up to elevation, and just took the height of A across, and that gives me my line AB, which is here. Because as we said, B didn't move. So in other words, the line AB now, I'm looking directly at it, I can see the true length of the line and the true inclination between it and the ground, which is here. So either method is fine. The second method is just a little bit quicker. Question A3 is a conic sections question, specifically a hyperbola question. So what they're saying is when you top a pencil, these little curves that are here map out hyperbolas, and they're going to draw a hyperbola. They're basically using that as the example. So the drawing on the right shows an axis AA1, directrix DD1, and the focus F is given for one such hyperbola. The hyperbola has an eccentricity of 3:2. That is really important. Locate the position of the vertex and draw the portion of the hyperbola. So straight away, when I know eccentricity has been mentioned, I always write down F to P over P to D. So from the focus to a point on the curve, divided by the point in the curve to the directrix. And that equals, in this case, 3:2, which means 3 over 2. So F to P is 3 units, P to D is 2 units. So from any point on the curve, from F it will measure 3 units. So for example, if F to a point in the curve was 30 millimeters, the distance from that point to the directrix would be 20 millimeters. So that's where the 3 and the 2 comes in. The vertex is also a point on the curve. So in other words, F to P, which will be the vertex, will be 3 units, P to the directrix will be 2 units. I can take this distance and divide it into 5 units, 3 units plus 2 units. So divide that into 5. If it's an easy measure, I can measure it. So in other words, my distance I have here is 15 millimeters. So they've left it pretty handy. I can divide it up into 3 millimeter sections. So 3, 6, 9, 12, 15. That gives me 1, 2, 3, 4, 5 equal sections. F to P is 3 units. 1, 2, 3 units. So this is the point P, which is the vertex. P to D is 1, 2 units. It gives me the vertex. And when I have that done, it's pretty straightforward. I will have my eccentricity line up here. To find a point on the eccentricity line, 45 from the focus. Sorry, the wrong way around. My mistake. So I've got my 45 degree line from the focus, and I just simply come vertical from the vertex. Where those two cross gives me a point on the eccentricity line. That is my eccentricity line, and now I can use my normal conic sections construction. So I'm going to divide this up. I'll pick some divisions. It doesn't really matter where I put them, so I'll take, for example, 1 between the vertex and the focus. I'll take another one here, another one here, and I might just do 3 outside it. My method is always the same. So I've got my focal line, vertical line through the focus. Each of these points I'm going to take up to hit the eccentricity line. So up to hit the eccentricity line and back to hit the focal line. And I can do it above and below the line here. And with my compass at the focus, I take my point, swing it around, and on the bottom. That gives me 2 points in the curve. Same for the next one. I can come up to hit the eccentricity line, across to hit the focal line. Again from my focus, swing the point around. Point on top, point on the bottom. I'll do the second point off screen. So I found 3 points on the top and bottom. Always remember the point directly above the focus where that hits the eccentricity line is a point, so I can take that above and below. And then the last point is just going the opposite direction, but it's the same method. Take my point up to the eccentricity line back to hit the focal line and draw my curve. So compass, swing the point out, swing the point out. That gives me my points. I'll draw on the curve now. Okay, now I've drawn the full curve. You'll see in the question it said it's only necessary to draw one branch, but I wanted to show you the full construction if it comes up in another question. Last part then, the second part, locate a point P on the curve which is 60 millimeters from point P. Locate a point P on the curve which is 60 millimeters from the focus, rather. So all I have to do is take a distance of 60 on the compass. Distance is 60, and from the focus I'll find a point P. So point P out here, and I'd have to go take another point. I'm just going to draw a freehand to save time. So I've located a point which is 60 millimeters, and that's point P. I have to draw a tangent. Our same construction for all these questions can be used. In other words, P to the focus, and I'm going to come off at 90 degrees. So I come off at 90 degrees from the focus. The point where it cuts the directrix is a point on the tangent. So P back is my tangent. There is my tangent. So again, join to the focus, 90 degree angle here. And that's to draw a tangent. I can use that method for ellipse, parabola or hyperbola. Question A4 then. So this is basically an elevation plan end view question. It's based on the shape of a cube that's inclined to the horizontal and the vertical plane. We have to complete the elevation of the cube and then draw a plan of the smaller sphere that would contain the cube. So in other words, we have to build a sphere outside the cube. We'll get back to that. First thing we want to go doing is drawing the elevation of it. Now, when it's an elevation plan question, this is pretty much testing what you know about elevation plan, end view and elevation. In other words, the main thing here is that we can copy heights from auxiliary elevation to original elevation. The first thing I'd be doing here is labeling the drawing or labeling the cube so you can try and make a little bit of sense of it. I'm going to shade the main surfaces that you can see different colours just so you can make a bit more sense of it as well. I've labelled up the three main surfaces that you can see, so the one towards the front and the one towards the left and the right. I'll label them too. 1, 2, 3, 4. I call these 2 points 5 and 6 and this point 7. There's only one point left on it, and that point you can see where the 3 points converge, or 3 lines converge, so it's in underneath number 2, number 2, yeah. So 2 and 8, it's going to be needed later, but 2 and 8 is a vertical line, so we can take that vertical. The reason I've labelled it is so I can find the points in the auxiliary elevation first, then in the elevation. So I can bring up, here's point 1, here is point 4, point 2, and I'm going to bring up all the rest of these points to find them in position. I'm going to label up points 1 to 8 on this cube in auxiliary. Okay, so point 3 when I bring it up is here, 7, 6 is at 3, 2 and 8 are along the same line, so there's 8, I have 2 already labelled, and I'm missing one point number 5, 5 is here. What that means now is that I can take all of my heights. I can take the height of 1, the height of 4 and 5, the height of 2, and I can bring those to elevation. So if I come along and take up my points into elevation, I'll be able to find each of my heights. It's already kind of started for me, but I've kind of ignored that. So just to show you how the whole question would have been done. I can start by building up each of the points. Now, the points I'm going to see towards the front, 1, 2, 3 and 4. I'm going to see those towards the front because they're lowest in the plan view. I made a mistake in my initial labelling, so point 8 is on the bottom, point 2 is on the top. So 1, 2, 3 and 4, I see surface 1, 2, 3 and 4. I'll take up those points. So the height for 1 is my height for 1, and I've taken my point already up. That gives me this position of 1. Height of 2, again take up the height of 2. Height of 3, again take up the height of 3. And point 4. height of 4 is brought up, and they've already got that for me. So I can draw in that surface now, 1, 2, 3, 4. I can keep building up surface by surface, so when I take point 2 up, I'm looking here at 1, 4, the surface there. I take point 2 and 8, we're on the same position, so when I take up, I got 2 above here, 8 we said is directly below, so here's point 8. And point 5 is already brought up for me. So in other words, I can draw in that surface as well. Make sure your edges are parallel. So I've already got an edge drawn in here. This is a cube, so the lines need to be parallel to one another. So when I come along, that edge should be parallel, which it is. So I've got 2 surfaces drawn in. I need to find another point under here. So I've got the surface 3, 4, 8, and I see here my surface is 3, 4, 8, 7. So 7 should be the other one I need to find. When I come along, I take up 0.7. And even if I didn't do that, so here's my 0.7, even if I didn't do that, I can use my parallel lines to find the points. So in other words, when I come along, 3, 7 should be parallel to my 4, 8 line. Likewise, my line here should be parallel. And it is. So I didn't actually have to go find 0.7. When you get this cube started, you can start to draw on all the lines. Now I've got all the points of the cube there. Second part of the question was find out the sphere that will be contained. So to find the surface out the side here, there was 2 methods of doing it. I had 0.8 on the bottom. I can just come parallel to 4, 3 and hit my construction line. And likewise, I can come parallel to 4, 8 and hit my construction line. Alternatively, I could just, as I did before, copy the height of 7 and bring it up. Here's my height for 7. That gives me the shape of the sphere. They've asked us to build a sphere around the cube. To do that, I need a real length of a diagonal. The only real length of a diagonal I can see is from 2 to 8. It's a vertical line, so from the very top point down to the very, very bottom point. And I have that in elevation. Because it's a vertical line, I see the true length of it in my elevation. And so it means this is actually very straightforward. I can just take half the distance I could also bisect it if I wanted to be even more accurate, but it'll save you more time in the leaving it this way. And in other words, I can just draw my circle around it. So using any of the diagonals would have found that. That is my sphere drawn in elevation, and I can draw the sphere in plan as well if I want. What you may have spotted too is that the line 1, 7, when we're projecting out our auxiliary elevation, the diagonal 1, 7, we're looking at 90 degrees to it, meaning that's also a true length. So I also had the option to take diagonal 1, 7, find the center of it, and I could draw that circle in my view here. So that is the same circle. And again, I could have just taken my height for the center and brought it back down and up and drawn the center in elevation.